Getting an LLM to respond is only step one. The real engineering challenge is making every token economically efficient. In this module, we'll connect quantization, batching, and GPU utilization to latency, reliability, and cost per request. So far, we've moved from symptoms to control. We diagnosed why naive LLM systems fail: runaway token spend, latency spikes, out-of-memory errors, and drift. Then we introduced owned models and vLLM serving. Now we'll focus on the economics of inference, using quantization, batching, right-sized hardware, and monitoring to make GPU serving predictable, efficient, and ready for routing and auto-scaling. Self-hosting only saves money when the GPU is doing useful work most of the time. The hourly rental price is just one part of the equation. What matters is how many high-quality tokens you produce from that hour. Low utilization, poor batching, or wasted memory can make an expensive GPU cost more than an API. Optimization means tuning the serving stack for throughput while protecting latency and reliability. It also means measuring cost by workload, because chat, summarization, and batch generation stress the system in different ways. Quantization is one of the main levers for reducing serving cost. Instead of storing weights in FP16 or BF16, we represent them with fewer bits, commonly INT8 or INT4. That shrinks VRAM needs, so the same GPU can hold a larger model, serve more simultaneous requests, or run bigger batches. The trade-off is precision. Lower bit formats can introduce quality loss, and they usually require calibration, testing, and compatible kernels. Smaller also does not automatically mean faster. Latency improves only when the hardware and serving engine can use the lower precision efficiently. Think of quantization as a cost-quality dial. With 8-bit, you usually get a strong reduction in memory use while keeping behavior close to the original model, so it is often the safer first step. With 4-bit, VRAM drops much further, which can enable larger models or cheaper hardware, but the risk of weaker reasoning increases. Be especially careful with math, code, long context, and precision-heavy domains. The practical rule is simple: benchmark with real prompts before choosing the smaller format. The serving stack matters just as much as the quantized model. Methods like AWQ, GPTQ, SmoothQuant, bitsandbytes, or FP8 each produce formats that depend on the runtime and hardware underneath. After conversion, ask one question first. Does your serving stack have optimized kernels for this exact model and format? If not, a smaller model can actually run slower. Validate support in vLLM or TensorRT, check GPU capability, then benchmark both latency and output quality. Memory savings only matter if the deployed system is faster, stable, and still accurate. Cost per token is how self-hosting becomes comparable to an API bill. Start with total hourly infrastructure cost, then divide by how many tokens the system actually produces in that hour. Multiply by 1 million to get a business-friendly number. The hard part is the denominator. Tokens per hour changes with batching, utilization, request mix, context length, and whether work is prefill heavy or decode heavy. And do not count only GPUs. Include CPU, memory, networking, storage, monitoring, orchestration, and engineering operations. Once you have this number, compare it to provider pricing and to revenue per user. Let's put that cost model to work. A GPU priced at $3 per hour becomes $3.90 after 30% overhead. If it serves 2,000 tokens per second and stays 70% utilized, it produces about 5.04 million tokens each hour. Divide cost by output, and inference lands near 77 cents per million tokens. But if throughput drops, the same hardware can cost several dollars per million. Utilization and throughput dominate the economics. Before optimizing cost, measure what the system actually delivers under realistic load. Track tokens per second, requests per second, time to first token, and end-to-end latency, ideally at P95, not just averages. Use production-like prompt lengths, output lengths, concurrency, and sampling settings, because each one changes GPU behavior. Separate prefill from decode as well. Prefill processes the prompt and is often bandwidth heavy. Decode generates tokens step by step and stresses latency differently. Then compare each candidate configuration: model size, quantization, GPU type, and batching. Only then does cost per million tokens mean anything. GPU choice is not a contest for the biggest card. It is a matching problem. A smaller GPU can be the cheapest reliable option when the model is quantized, traffic is light, batches are small, or latency requirements are relaxed. A larger GPU earns its cost when you need more VRAM, longer context, higher memory bandwidth, or many simultaneous users. The key is to model the workload, model size, context length, batch size, latency target, and traffic spikes. Optimize for acceptable quality and reliability at the lowest total cost. Start with the simplest serving shape that works. If the model fits in one GPU's VRAM and latency and throughput meet your target, single GPU serving is usually the best default. Fewer moving parts, easier debugging, and lower base cost. Tensor parallel serving becomes useful when the model is too large, or when one GPU cannot deliver enough throughput. But the model shards must constantly exchange activations, so fast interconnects and good placement matter. Use multi-GPU deliberately when the memory or performance gain outweighs communication overhead and operational complexity. The cheapest path is not always the lowest GPU hourly rate. Self-hosting can win when demand is stable and your team can handle serving, monitoring, scaling, security, and incidents. Managed inference is often better for bursty traffic, fast launches, or teams that do not want infrastructure ownership yet. A hybrid model is common. Run predictable baseline load on your own capacity, then spill bursts to a provider. Compare total cost of ownership, including engineering time, reliability risk, idle capacity, latency control, and how quickly demand changes. GPU utilization is a direct input to cost per token. If an expensive accelerator is only doing useful work 20% of the time, the idle 80% is still being paid for, and that cost gets loaded onto every token served. But the answer is not blindly chasing 100%. Saturated compute, memory, KV cache, or queue depth can push requests into waiting, raising P95 and P99 latency or causing timeouts. The healthiest target is sustained high utilization, often around 60 to 80%, while still meeting latency SLOs. Batching is one of the biggest levers for serving efficiency. With static batching, the system waits until enough requests arrive. Throughput improves, but quiet periods can add unnecessary latency. Continuous batching changes the model. As soon as one request finishes a decode step, another can enter, keeping GPU slots filled even when request lengths vary. Consolidating safe workloads across tenants, models, or priority classes increases the pool of demand, which makes batching more effective. Autoscaling then handles longer trends. Add GPUs when demand stays high and remove them when traffic drops. Efficient LLM serving comes from disciplined measurement, not guesswork. Quantize and batch only after checking quality, latency, and compatibility. Compute cost per token from real throughput, utilization, overhead, and traffic shape. Right-size hardware to the model, context, concurrency, and SLOs, then keep monitoring utilization. Next, this foundation supports routing, fallback, auto-scaling, and capacity planning.